The ocean is the largest and most mysterious feature of our planet, covering more than 70% of Earth's surface and holding about 97% of all its water. Beneath its shimmering surface lies a vast and complex world of chemistry, motion, and energy. Every drop of seawater is a miniature universe, filled with dissolved minerals, salts, gases, and microscopic particles that interact in constantly shifting patterns. The ocean's salinity averages around 3.5%, but this value is never constant. It changes with evaporation, rainfall, melting ice, and the flow of rivers. Temperature, too, is far from uniform. Near the surface, sunlight warms the upper layers, creating what scientists call the mixed layer, where heat, wind, and waves blend water into a dynamic soup of motion. Beneath this, temperatures drop sharply in a boundary region known as the thermocline, and deeper still, near the seafloor, waters can reach just above freezing. Pressure increases by about 1 atmosphere for every 10 meters of depth, turning the deep sea into an environment of unimaginable intensity, where even metal and rock behave differently under crushing weight. The color of the ocean is shaped by light itself. Sunlight penetrates the water column, but the red, orange, and yellow wavelengths are absorbed quickly, leaving only shades of blue and green to scatter through the depths. This is why the sea appears to shift in color depending on time of day, clarity, and depth. Waves are born from the friction between wind and water, transferring energy from the atmosphere to the ocean's surface. These ripples can grow into rolling swells that travel thousands of kilometers across open water, carrying energy long after the winds that formed them have faded. When these waves reach shallow shores, they slow down, rise, and finally break, releasing their energy in a rhythmic pulse that shapes coastlines over centuries. Beneath the waves, the seafloor is as varied as any landscape on land. It features towering mountain ranges, called mid-ocean ridges, where molten rock from Earth's mantle pushes upward, creating new crust and expanding the ocean floor in a process known as seafloor spreading. Deep trenches, some plunging more than 11 kilometers, mark places where old crust sinks back into the mantle. Between these extremes lie vast plains of sediment, built grain by grain, from the slow rain of particles drifting down through the water column. Volcanoes, hydrothermal vents, and undersea geysers release heat and minerals, turning the deep ocean into a living laboratory of chemistry and geology. The circulation of seawater driven by temperature, salinity, and wind forms a global conveyor belt that connects every ocean basin. This immense flow, known as thermaline circulation, moves heat around the planet, helping regulate climate and weather patterns. Beneath the waves, the seafloor is as varied as any landscape on land. It features towering mountain ranges, called mid-ocean ridges, where molten rock from Earth's mantle pushes upward, creating new crust and expanding the ocean floor in a process known as seafloor spreading. Deep trenches, some plunging more than 11 kilometers, mark places where old crust sinks back into the mantle. Between these extremes lie vast plains of sediment, built grain by grain, from the slow rain of particles drifting down through the water column. Volcanoes, hydrothermal vents, and undersea geysers release heat and minerals, turning the deep ocean into a living laboratory of chemistry and geology. The circulation of seawater driven by temperature, salinity, and wind forms a global conveyor belt that connects every ocean basin. This immense flow, known as thermaline circulation, moves heat around the planet, helping regulate climate and weather patterns. Sound travels differently underwater, moving almost 5 times faster than through air. Because of this, the ocean is a world filled with echoes and vibrations. Waves breaking, ice cracking, underwater landslides, and even the distant rumble of undersea earthquakes all create a vast and complex soundscape. The ocean floor itself is constantly changing. Tectonic movements shift continents, volcanic activity builds new islands, and sediment carried by currents reshapes underwater valleys and ridges. In some places, methane and other gases seep from the seabed, forming shimmering bubbles that rise slowly to the surface. The ocean is also a vast carbon sink, absorbing nearly a third of the carbon dioxide produced by human activities. This absorption slows global warming, but also alters the chemistry of seawater in ways we are only beginning to understand. Plastic pollution, nutrient runoff, and microfibers have become new layers in the ocean's story, drifting through currents and accumulating in places like the Great Pacific Garbage Patch, an evolving reminder of how deeply human activity now reaches into marine systems. Even time itself behaves differently in the ocean. Sunlight fades within a few hundred meters, plunging most of its volume into perpetual darkness. Currents can take centuries to complete a single circuit from surface to depth and back again. Minerals forming on the seafloor may take thousands of years to solidify, while tectonic shifts reshape entire basins over millions. The ocean is both ancient and alive, in motion its waves, chemistry, and circulation recording the memory of our planet across geologic time. Every ripple, current, and drop of salt water is part of a system so immense and interconnected that even the smallest change can ripple across the globe. The story of the ocean is one of balance and transformation, heat becoming motion, rock becoming liquid, and water becoming vapor before returning to its source. It is the beating heart of Earth's climate, the mirror of the sky, and the memory of deep time. To understand the ocean is to understand the planet itself, a living system of water, energy, and motion that sustains everything above and below its surface, silently shaping the world with every tide and wave. The ocean is also the planet's largest chemical mixer. It contains dissolved salts, gases, and minerals that support countless natural processes. The average salinity is about 35 parts per thousand, though this value varies depending on evaporation, rainfall, and proximity to rivers or ice. Ocean currents, both surface and deep, constantly move this water around, redistributing heat from the equator to the poles and shaping the world's weather patterns. The global conveyor belt, a system of interconnected currents driven by temperature and salinity differences, can take more than 1,000 years to complete a single circulation around the planet. This massive system not only affects climate, but also influences nutrient availability and the cycling of carbon and oxygen. The ocean absorbs around a quarter of the carbon dioxide produced by human activities each year, buffering the effects of climate change, though this absorption also leads to a gradual increase in acidity. A process known as ocean acidification. Sunlight penetrates only a small portion of the ocean, roughly the upper 200 meters, creating what is called the photic zone. Below this, light diminishes rapidly until complete darkness prevails. The deep ocean, which makes up the vast majority of the marine environment, is characterized by crushing pressure, near-freezing temperatures, and total absence of sunlight. Yet even without light, incredible chemical and geological processes continue. In these depths, sediments slowly accumulate, composed of fine particles, minerals, and microscopic remnants that settle from above. Over millions of years, these sediments form thick layers that record Earth's history, capturing changes in climate, volcanic eruptions, and even meteor impacts. The ocean is also a symphony of sound and motion. Waves, tides, and currents constantly reshape coastlines and influence the distribution of energy across the globe. Tides are driven by the gravitational pull of the moon and the sun, creating rhythmic rises and falls of sea level that affect nearly every coastal system. Storms, particularly tropical cyclones and hurricanes, draw their energy from warm ocean waters, illustrating the tight connection between ocean temperature and atmospheric behavior. In fact, the ocean stores about 1,000 times more heat than the atmosphere, making it the most powerful driver of Earth's climate system. Even subtle changes in sea surface temperature can influence rainfall patterns, droughts, and wind circulation thousands of kilometers away, as seen in events like El Niño and La Niña. Beyond its visible surface, the ocean is a vast reservoir of resources and potential. It contains immense quantities of dissolved minerals, such as magnesium, lithium, and even traces of gold. The seafloor harbors deposits of polymetallic nodules and hydrothermal vent, minerals that some nations are now exploring for future extraction. Its water also holds untapped potential for renewable energy. Waves, tides, and currents could collectively generate significant amounts of clean power. The ocean's microbial communities, though invisible to the naked eye, drive much of its chemistry, producing oxygen, recycling nutrients, and forming the foundation for all higher processes. Every drop of seawater contains an entire microscopic ecosystem interacting in complex, dynamic ways that scientists are only beginning to understand. In a very real sense, the ocean is not just a body of water, it is a living, breathing system that connects every part of the planet. It influences the air we breathe, the weather we experience, and the future we shape. Even without mentioning its inhabitants, the ocean itself remains one of Earth's most powerful, mysterious, and life-giving forces. The ocean covers more than 70% of our planet's surface and contains about 97% of all the water on Earth. Its depths can reach over 36,000 feet, with light only penetrating a few hundred feet below the surface before giving way to darkness. In these deep zones, the temperature can plummet to near freezing, and the pressure becomes immense, so great that it would crush most human-made structures without special reinforcement. Yet the ocean's waters are not static. They constantly circulate through vast global systems known as currents. These currents act like conveyor belts, carrying heat, nutrients, and dissolved gases across the planet. For example, the Gulf Stream transports warm water from the Caribbean up the Atlantic, influencing the climate of entire continents. Ocean currents also play a crucial role in regulating weather patterns, stabilizing temperatures, and driving the water cycle that sustains life on land. The chemistry of seawater is equally fascinating. It's a complex mixture of salts, minerals, and dissolved gases, primarily sodium and chloride, but also magnesium, calcium, potassium, and trace elements like iodine and iron. These components help maintain the balance of life on Earth and even influence the formation of clouds through the release of sea spray into the atmosphere. The ocean also serves as a massive carbon sink, absorbing around a quarter of the carbon dioxide produced by human activity each year. This process helps slow the rate of global warming, but also leads to ocean acidification, a subtle yet powerful change in pH that can alter ecosystems at the microscopic level. The ocean floor, meanwhile, is a dynamic landscape filled with geological wonders such as deep-sea trenches, vast plains, and mid-ocean ridges that stretch for tens of thousands of miles. At these ridges, tectonic plates diverge and magma rises to form new seafloor, continuously reshaping the planet's crust. Hydrothermal vents found along these ridges release superheated, mineral-rich fluids, creating environments unlike anywhere else on Earth. Beyond its physical and chemical characteristics, the ocean also produces over half of the world's oxygen through the activity of microscopic organisms that live in its upper layers. These tiny life forms drive the planet's oxygen cycle and form the foundation of marine food webs. The ocean's surface is also where the exchange of energy between water and atmosphere fuels storms, hurricanes, and even global climate systems like El Niño and La Niña. In addition to its natural processes, the ocean is a vital resource for humans. It supports trade routes, provides food and energy, and holds untapped potential for renewable power through waves and tides. However, it is under growing pressure from pollution, plastic waste, and rising temperatures. Every minute, an estimated truckload of plastic enters the ocean, where it can persist for hundreds of years, breaking down into microplastics that circulate through the currents and even return to us through rainfall and the food we eat. Beneath its shimmering surface, the ocean is not just a vast body of water, it's a living, breathing system that connects every aspect of our planet. It regulates the Earth's temperature, shapes the atmosphere, and drives the natural rhythms that sustain life everywhere. The deeper we study it, the more we realize how essential its health is to our own survival. Every wave, every drop, and every unseen current plays a role in the delicate balance that keeps our planet alive. The ocean is both ancient and ever-changing, a reminder that our world is interconnected through the unseen power of its depths.